Hi guys, my name is Vishy Kasar, and I work in Apple that provides infrastructure service for rest of Apple. First thing, everybody needs to wear the headphone. It has to be blue color for listening to me today. I think I see most of it is blue. So when I mentioned to my colleagues on, hey, I'm going to be talking about Redis replication, so they asked me, why are you talking about Redis replication? You know, it just works. It's been around for quite some time. It's very well documented, and it's not the newest shiny thing. And if you're unable to hear me at any point, can somebody just say this, and I can get someone to help? So the reason why I decided to talk on Redis replication is I've been fairly new to Redis. Redis has been around for about 10 years, and I've been working on it for about 2+ years. When I started with Redis, I thought I kind of knew how the Redis replication works. And as I started supporting more and more Redis in production, then I realized I knew it at the surface. And there's this huge treasure trove. When I dig deeper, there's so much to know about Redis replication. And today I'm going to share some of that with you guys. I cannot promise that each one of you will learn everything new here, but if at least some of you take something new at the end of this talk, I feel happy about the time I spent on it. So here's a quick agenda. I realized that when you have audience like this, you are at various levels of Redis maturity. So I want to spend a bit of time in the beginning just talking about how replication works, and then we will move on to some of the Redis configuration, monitoring options. Then I want to dive deeper into two important topics, which is data consistency with Redis replication, and then memory usage with Redis replication. I'm going to share some of the common replication issues that I see every day, and we're going to top it off with a demo. So replication basics. We have Redis has this Redis Master and Replicas. So as a client, you generally write to the Redis Master some data, and then that data asynchronously replicates to the replicas. You can have more than one replica. And then from that point onwards, client can actually read from the replicas, or it can also read from the leader. Pretty straightforward. So along with the replication, generally you have a Redis failover service. It could be Sentinel or something else. It's a kind of monitoring your Redis masters and Redis replicas. So if the master dies, then it can actually promote an existing replica to the new master. So this is generally the idea. So what are some of the key facts? Replication is asynchronous in Redis. First key facts to understand. As a client, when you're writing data, you generally do not get to control when the data has reached the replica. Okay, all that you know is you're written to a Redis master, and the data gets replicated asynchronously. Replication is non-blocking on the master side. It's a very good thing, right? You don't want the replication that's happening on the master side to affect your client performance. You want Redis to respond to your reads and writes as fast as possible, irrespective of what happens. So that's why it's been designed to be non-blocking on the master side, and it's mostly non-blocking on the replica side as well. However, there are some windows where replica, when you make a read against the replica, you get the message saying, hey, I'm still syncing up with my master. I'm unable to serve your reads right now. Master can have any number of replicas, and generally replicas read only, but Redis allows you to provide a config option where you can actually make the replica take writes. So, but one key thing to remember is if you write to a replica, that write is local. It's not going anywhere else. Whereas if you write to the master, it goes to all the replicas. And also, the writes that you do to a replica can get overwritten when the next time replication happens from the master. If you write with the same key, when the data comes from the master, that your local writes gets overwritten. But it may be applicable for some use cases. But in general, by default, replicas are read-only. And replica can be master for other replica. You can have a chain. So this is super useful in the case where you have, let's say, 3 replicas in one DC and 3 in the other, and you have a master in one of the DCs. There's no point this master writing over the WAN to all the 3 replicas on the remote DC. So instead, what it can do is choose a local master in the remote DC, write to that, and then that master can then replicate to rest of the replicas in that data center. So what's the need for replication? First need, of course, is the high availability. Redis is a in-memory database. If Redis were to go down, you want someone else to immediately take the data and serve it. So you can serve this by having an in-memory replica. And there are instances where you need Redis replication for spreading the read load. And this happens, let's say you have some caching needs, and you can serve all your caching needs with a single Redis instance, and it can handle all the writes. However, the read transactions per second is so many that you cannot serve using a single Redis instance. So for such cases, again, you replicate your data and send all your read traffic to these replicas. So basically, you're spreading the read load across the replicas. That's the second need for replication. And the third one is interesting, where you do replication in lieu of persistence. So Redis, as you probably know, offers persistence, but persistence comes with its own baggage. You need a hard disk with your computer, more moving parts, more chances for failure. So there are some use cases where they don't want all these things, but they still need a copy or multiple copies of your data, and replication serves those needs as well. So what are the types of replication? Broadly, there are 2 types of replication. One is called full sync, and second one is called partial sync. And let me go over them. Full sync, as the name indicates, you're taking an entire dump from your master to your replica. All the data gets transferred. All right. How does Redis Master do this? And how does Redis Master do this in a way it doesn't affect the client performance, right? The way the Redis Master does is it forks itself into a separate process, and the fork process is then responsible for sending the data over to the replica. It can do it in one of the 2 ways. One way is the fork process can actually write to the disk, and then the disk file gets transferred over. And this is how Redis used to work a couple of releases ago. Now, there's also a diskless mode where the forked Redis master can actually write over the wire to the replicas, so you don't really need the disk on the master side. However, on the replica side, you still need a disk to collect this data so the replica can bootstrap. And obviously, you use the full sync when a replica is bootstrapping. It doesn't know anything, so it says, give me everything, master. I'll take all your data. That's when this happens. Also, when the partial sync, which I'm going to explain next, whenever partial sync fails, then you kind of go back to the full sync mode. Pretty straightforward. Partial sync basics. The key to understanding partial sync is there's this concept of replication backlog. Okay, in the master, it keeps certain amount of memory reserved for the backlog, and as and when new writes come in, the new writes are also kept in the replication backlog. With each byte that you write, you keep an offset, and that offset keeps increasing forever. And this buffer is not an endless buffer. It's a circular buffer, and it has a begin pointer of valid data and the end pointer, like a first byte offset and the current valid offset. And in between that is your valid data, right? So the replication offset is where I am at currently in the buffer. But you cannot take the offset by itself. There's this concept called replication ID. So when the master comes to life, he's given a unique replication ID. If the master restarts, he gets a new replication ID. And the offset kind of goes hand in hand with that replication ID. They're together. You cannot just look at offset and say, OK, I want that offset. You should always say, for this replica ID and this offset, I want to sync, right? And there's also this replica client output buffer. Redis is an in-memory database. Reading from memory is super cheap, but writing to the network is not cheap. So there's an impedance mismatch, right? And plus, Redis is single-threaded, so it wants to write as fast as possible to the client and then move on to the next work. However, you cannot write that fast to the network. And if you listen to Salvatore today, he mentioned how that is the slowest part of writing. So in order to bridge this gap, Redis has this concept of client output buffer. Essentially, whatever Redis wants to write back to the clients, it writes to these output buffers and then merrily goes on. And output buffer is then responsible for draining the data to the client. And your replica is nothing but another client from a Redis point of view. If you look at it, you're writing data to it or the network, right? So replica also gets a client output buffer. So that also plays a role in the partial sync. Now let's put it all together. So we have a client, and we have Redis Master and Redis Replica. And if I double-click on the Redis Master, of course, it has a key value store. That's the primary purpose of it. And it has a backlog circular buffer. And it also has this replica client output buffer that I talked about. Now, when the client writes some data, so that data, of course, you have to first store it in the key value store. That's the purpose of Redis. But right after that, the data is also written to this backlog circular buffer and to the replica client output buffer. And whenever the network allows, and maybe immediately, that data now gets returned to Redis Replica. And the data keeps getting drained from the client output buffer. But in the backlog, the data is actually kept for any other replica that will come back a bit later, who is out of sync. You have still kept that circular buffer. So quickly going over the replication backlog, you can control the size through the replica backlog size in your Redis configuration. And as I mentioned, there are two key offsets here. There's a first byte offset. It starts at 1, and it stays at 1 until your circular buffer becomes full. And when you start overwriting, then this starts increasing. And from that point onwards, it's an ever-increasing buffer. So then you have the master replica offset, which starts at 0. And with every byte that you write, it keeps increasing. Let's take a look at this using a quick example. So I have a replica backlog size with 50,000. And my first byte offset is 1. Let's say I write some 21K bytes. So my master replica offset moves. I write some more data. Now I'm near the end of my circular buffer. So I write some more data. My master replica offset moves to 52. It's an ever-increasing number. And look at what happened to my first byte offset, 2429, right? It has moved too. What is the significance of the first byte offset? At this point, if a replica comes and asks me, hey, master, give me 2,400, right? Then I'm going to respond saying, hey, I don't have it in my backlog. Go away, do a full sync, OK? So the valid data is always between the first byte offset and the replica offset. So now that we understood the replica backlog, I want to quickly go over some of the key configuration options. So first, how do you make yourself a replica of someone? Let's say we have two Redis instances. One is running at 7001 port on the local host, and a second one, let's say I'm running at 7002. If I want to be a replica of the 7001, I use a command such as replica of localhost 7001. And replica of no one is a keyword. where I say, previously I used to be a replica, but I no longer want to be a replica. I want to be a master now. So I can just issue the command replica of no one. Then I become a master. Okay? So then the replica backlog size that I mentioned, the default value of that is 1 MB that you can change. There's also this replica timeout. This has multiple meanings in Redis. One key meaning is on the replica side, when you're getting this data from your master, generally the data transfer has to finish within this time, which is 60 seconds. And if it doesn't finish within that time, then that connection is cut off. So this last one is the client output buffer limit. This is the other output buffer that I talked about for the replica. And it has a hard limit, by default 256 meg. And if the hard limit is breached, connection is closed right away. So what is the meaning of that? On the master, you're collecting some data to be returned to replica, and that replica hasn't even come back. So I do not have an endless buffer, right? So at some point I say, hey, I don't want to store the data anymore for you. I'm just going to cut off connection, and then free this buffer. And later you come back into full sync if you wish. So 256 meg by default is the hard limit. It also has a soft limit. In this case, it's by default it's 64 meg in 60 seconds. What this means is, even if the hard limit is not reached, if you're at 64 meg for about 60 seconds, that means you're unable to drain the data fast enough also. So even in that case, I'm going to close the connection on you and ask you to come back. So next, I'm going to make you go through some of the monitoring. There are two key commands. There is a Redis Role and info replication. So role is a very simple command. When you invoke role on a master, it simply says, I'm a master, I'm at this offset, and I have one replica in this case, and my replica is running at localhost, and my replica is running at this port, and here is my replica offset. And as you can see in this example, my master offset and replica offset are not the same, and replica offset is a little bit behind. What this tells you as a user is, when you go against the master, is that replica is a little bit behind, and it needs to catch up. Okay? And if I execute the same role command on the replica, it says, I'm a replica, I'm at, my master is at this IP, this port, and status is connected, and what's my offset. So info replication is the other command that you can use to monitor Redis. And we'll kind of, in the demo, I'm again going over some of these things. But let me quickly explain here. In the info replication section, the key thing to look at is how many replicas I have. And for each replica, what IP, what port the replica is running on, and what is the state, whether replica is connected, whether it's online or not, and the replica offset, which is again same information that was given in the role. And the last field there is the lag. Lag tells you when was the last time that this replica talked to me. Each replica talks to master by default at every second. So in a typical healthy production system, you see this number going between 0 to 1 all the time. But whenever a replica dies or the network connection gets broken, you see the lag increasing. Okay? And the next section I have is the unique ID I talked about, the replication ID for the master, replica offset, first byte offset, and the replica backlog size. In this case, I had set the replica backlog size to 50K. And we also have this backlog histlen that did confuse some of my colleagues. So it starts at 0, generally increases up to the your buffer size, and kind of stays there. So I haven't found much use myself. I'm sure there are some use that I do not understand. So info replication on the replica, again, as you can expect, it gives the replica's offset, where my master is, what's the replica ID. Key thing to remember is you are a replica of someone else if you both share the same replication ID. You can be at different offsets, and the job of the replica is to be as much in sync with the master, get to the same offset, but your replication ID has to be the same. That's the primary way you are a replica of some master. And then, for the replica itself, it gives the offset, first byte offset, and the replication backlog size. It is not necessary for the replica to have the same backlog size as the master. It can have a different one, and hence it can also have a different first byte offset. But your replica offset should be the same, or trying to be the same. There's also this master replica ID and a second replica offset that, when you see info replication, you see, what is this? Does any of you know what a second replica ID is? Just by a show of hands. OK, then I can talk about this. I mentioned that when you are a replica, you actually faithfully copy a master by having the replication ID of the master. But there are instances when you are a replica, you are promoted to be a master. Right? Now imagine there are 10 replicas, and you're one of those replicas faithfully copying a master, and all of a sudden you are made the master by a failover process. And immediately next, what happens? All these other 9 replicas, they come and hit you with, hey, I have this old replication ID. I want to sync with you. The way Redis used to deal with it in the past was, hey, I now have a new rep ID because my role changed. I don't know anything about your rep ID. Come do the full sync with me. But as you can imagine, it's very wasteful because they were already pretty much in sync. And an optimization in one of the recent Redis releases is to store your prior master's rep ID as a second rep ID and the prior offset as a second rep offset. So that way, the replicas that were connected to the previous master, when they come and hit you, the new master, you can still say, yeah, I got you. You don't need to do the full sync. You're already in sync, and life goes on. This is a pretty good optimization, especially when you have large number of replicas. So next, I want to dive into data consistency on replication. And let me start with an example. So let's say you have a client. It goes to Redis Master and says, hey, I want to set my balance to 10,000. All right? So now, if the client reads immediately from the Redis Master, give me that data, of course, it'll get 10,000. But with replication, things are a bit more complex. The client can actually go to a replica and say, hey, get me balance. But if the asynchronous replication, if it hasn't happened yet, then either you get this balance is not set, I don't know about the key, or you get the prior value of the balance, both of which are bad, right? And async replication can happen anytime. And as a client, you do not really know when that has happened. So now, is Redis a 100% consistent database? That's not one of the design goals of Redis. But there are still some things that you can do to what I call as the best effort consistency. Okay, I'm going to share some of the tips so that it'll be useful to you to reduce the window of inconsistency. Okay, the very first thing that you can do, if it is possible, is to read from the master. You always write to the master. Your data is fresh, current on the master. If you read from the master, then it's very likely that you will get the right data. Okay. However, does it guarantee you 100% consistency? No, because your master can fail. At that time, a replica can get promoted, and it's quite possible that the replica that got promoted did not have the last bit of the write. So boom, there is inconsistency. But you have reduced the window of inconsistency by reading from the master. It may not be possible for all use cases. What if your reads are so many that you cannot achieve it through the master, right? In which case, you have to go to the replica. But this is a choice for some use cases. There's also this Redis server config called min replicas to write. And when you see this name, min replicas to write, you think, oh, boom, there's a good option I can use. Let's say if I have 2 replicas, I'll set this to 2. And as a client, I will come to know when those are written to these many replicas. but unfortunately, that's not what it means. This always goes with the second parameter here, which is min replicas max lag. What this means is if I'm a master, if a write comes to me, then I'm going to look at all the connected replicas and look at their lag. Now, if there are minimum number of if I have minimum number of replicas that have a lag less than min replicas max lag, then I'm going to accept that write. What it essentially means is, I have so many replicas that are connected to me with, not so much lag. I'm going to accept this write, but I'm not going to guarantee that the newly written data is going to those replicas. I'm just going to, give you some promises that I have these connected replicas, but I'm not going to promise you. Okay. Again, not 100% consistent, but you're reducing the window. If there are some replicas that are like totally out of lag, then as a master, you continue to say, hey, I cannot write your data because I do not have enough replicas with the sufficiently lower lag. So the next option that you have as a client is this great command called wait. So you can say as a client, you write some data, and you want to wait until that data reaches these many replicas. But of course, Redis is a distributed system. In any distributed system, things can go wrong. You cannot wait forever. So there is a timeout millis. So as a client, you can say, I wrote this data, and I want to wait this long, or until these many replicas have got my data. Okay, but key thing to remember here is you have to do the call on the same connection. I know this confuses people, some of the beginners. The reason is, when you're using a good client library, which does the connection pooling, you do not know exactly on which connections things are going. So if the wait goes on a different connection, then you get the wrong answer. Okay, so it's the key thing to remember here is you need to do this on the same connection that you actually did the set on, or whichever operation on, to get the right answer. This last one is interesting, and we employed it a couple of times. This is a case where you have a cooperative loader client. So let's say I have a loader client. I want to load my master with some data. Generally, I want to load it as fast as possible, but not so fast that there is an inconsistency. So what we did in this case is this loader client, loaded some data. Then, every few milliseconds, it gets replication offset from master, replication offset from my replicas, and compare. Are they sufficiently in sync? Yes. Then I continue my next batch of write. This is again another tool that you can use when you have cooperative, especially loader clients. So next, I want to dive into a very key topic, memory usage on replication. The job of the Redis is to store your keys and values. So you need large amount of Redis memory is used for that purpose. Then there's this backlog buffer that I talked about. And Redis has this max memory setting. What I want to explain here is the max memory actually is divided between the replica backlog buffer and the memory used. Okay, let me show that with an example. Let's say I set the max memory to 10 meg, and I set the backlog buffer to 5 meg. So what that does is the user space available is now only 5 meg. Again, key thing to remember. Now, again, when you run Redis in production, you set max memory to some value, let's say 10 gig, and occasionally you see process is taking more than 10 gig. So why is that? So here's the reason. I talked about this replica client output buffer, and that buffer size is not counted in max memory. Okay, that is in addition. All right, and then is the replica client output buffer the only buffer that Redis uses? No, actually it uses such buffers for every client. So there are other clients, and there are other buffers. So your actual memory usage of the whole process is like a total of this. If you have to take one thing away from this talk, I want it to be this. I haven't seen this picture in Redis documentation. Redis documentation is great. I love it, by the way. But I think this kind of puts together how the various buffers kind of play a role into your process size. Because when you operate Redis in production, one of the frequent things is, why the heck is Redis overshooting my max memory, and what can I do to tweak it down or tweak it up? So some of the key points is, replication backlog is a single circular buffer that's shared across all the replicas. And you should remember that it reduces the memory available for user keys, right? So as I mentioned, if you specify a max memory of 10 gig, and if you make this 5 gig, then your user memory is going down there. And the replica client output buffer is one buffer per replica. If you have multiple replicas, then each one of them gets a buffer, and by default it's 256 meg. So if you have 10 replicas, it can easily add up. All right. So again, key thing to remember when you're running Redis in production. And this client output buffer has a hard and soft limit, like I explained, and it increases the memory used by the process. So this is my last slide before I dive into demo mode, where I demonstrate some of the things that we learned today. So I just wanted to share some of the common replication issues that you see in production. One common thing is, your full sync fails. This is a common message. Fork was unable to allocate enough memory. And this is very common when you host multiple Redis instances per host, right? So what is happening here? As I mentioned, when Redis does a full sync, it has to fork itself. When you fork, the fork process needs some memory, right? How much memory does it need? Let's say I have a Redis master of 10 gig. Do you need another 10 gig when you fork, right? Actually not. With the modern operating system and copy on write semantics, all the memory pages are shared between your master and replica as soon as the replica, sorry, not the replica, with the fork process. So only on modification, the more and more memory gets used up. So it is possible to actually fork your process with minimal amount of memory. But then can you leave no memory? That's kind of too adventurous and too risky, right? Can you leave as much memory as needed by your master? I think that's like too chickening out, right? So you need to find a middle ground. And also you need to understand your data characteristics on how your data is getting accessed. Is the data getting accessed in such a way that maybe single memory page is getting updated repeatedly, or it's going all across all the memory pages, in which case the memory needed for the fork process is much higher, right? So those are some of the decisions that you have to make. And even after you make those decisions, there's this key thing called overcommit memory. And by default, it is 0. What that means is, if I'm a master of 10 gig, when I'm about to fork for full sync purposes, unless I have the 10 gig, OS does not let me, which is kind of not good for Redis. So you should set this overcommit memory to 1. What it says is, yes, I'm a 10 gig master, but I understand everything about copy on writes, and I know that I need lesser memory. So I'm just giving a hint to the OS, please launch me. I know what I'm doing. Okay. So I think for Redis, even I think when you start up, it says please set your overcommit memory to 1 if it detects that it's been set to 0. It's just it's really really essential. So other common thing is replica gets a timeout receiving the full sync data from master. This we have seen in production where your data set is so big, and for whatever reason network connection was not that great. So such cases it times out. So obvious answer is increase your replica timeout or reduce your data size, full sync data size. This last one is partial sync fails with a message client scheduled to be closed ASAP. And this happens when your client output buffer that I talked about is buffering the data for a replica. It gets overwhelmed. So the master decides, I'm not going to keep the data anymore. I'm going to just shut down this buffer and close your connection. Okay? So these are some of the common problems. And when that happens, the last one, so one obvious option is to increase your client output buffer size. Again, none of the buffer is endless. They all have a cost. So many of them are trade-offs. Okay? So next, I'm going to dive into the demo mode. So you guys can, everyone can see the terminal, right? Okay. So for my demo, so I'm going to have 2 Redis instances, my master running at 7001 and my replica running at 7002. And we're going to show a bunch of things, okay? So I'm going to first start the master. Master is starting in port 7001. It's ready to accept connection. We do not have any replicas yet. So I'm now going to show me the role of the master. RC1 is my shortcut for Redis CLI port 7001. So it's going against port 7001 and asking for the role. As expected, it's a master. And it's set offset 0 because we have not yet written any data. And the last line you see there is an empty list because I do not have any replicas. So let's fix that. Let's start the replica. So replica started. And I want to quickly show you what happened here. Replicas is trying to do some partial synchronization. It was not possible. Then it did the full sync from the master. The thing that you see with the 4.8 blah, 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 so that's the unique replication ID of the master. And the 0 that comes at the end is the offset. And it received some standard bytes in the beginning because there's no real user data. So far, everything is good. So now I come back here and say, hey, master, show me your role again. So master says, now I'm still the master, still offset is 0. Now I discovered a new replica, and replica is running at 7002. Pretty obvious, OK? So let's now move on to the other monitoring command, Redis CLI info replication. This is the command that I ran. And this pretty much shows all the things that I described before. I have one connected replica, and the port is 7002. It's online. Offset is 0 of the replica, and lag is 0 because we are well connected. Okay, so far everything is happening OK. And the master replica ID starts with 4A. Remember this because it'll come back. Replica ID 2, we don't bother right now. Replica offset is 0. Okay, and my first byte offset, as I was showing in the slide, is 1. All right. Now let's start to do something interesting with this. So I have this loader client. It loads number of keys, and with each key, I'm going to write about 1,000 bytes. Okay, let's write one key with 1,000 bytes, and let's see what happened here. And this loader client also does a info replication on the master. As you can see now, it wrote about 1,000 bytes, but my replica did not have time to catch up. It was still at offset 0. That was because I did this info replication as soon as I wrote. But has it caught up right now? So if you now see, master replica offset is 1023. My replica is also at 1023, and my lag is 0. Okay. So now let's start writing some more data. I want to bring it very close to the end of my replica backlog size. My replica backlog size, remember, it was 50K. So I'm near the end of that circular buffer because I wrote about 49K. And my first byte offset is still 1. So how about if I just write one more key, what happens to my replica offset? So master replica offset is ever increasing. So it went beyond my circular buffer. But look at what happened to my first byte offset. That also moved now. because the first 23 bytes have been overwritten, right? So at this point, if some other replica were to come to my master and say, hey, give me at byte, I'm at offset 20, I'm going to say, no, I don't have the data for you, all right? Now let's see what happens if I load 50,000 more. I just want to show you guys what happens to the first byte offset. First byte offset is ever increasing from this point because I'm beyond my circular buffer size, all right? So, so far we showed how things are working with the offset, but nothing bad is happening, right? Because the sync is happening, the connection between my master and replica is going good. So let's start to introduce some instabilities. So I have this stop replica command. As you can see, it's going to send a kill stop. So when you send this signal, your replica is still running, but it stops responding to anything. Okay, so this is a level of instability I'm going to introduce. And at this point, I'm going to write a key to my master. So I wrote some data. The first thing to notice here is lag is increasing. It is 24. We never saw this before. We are seeing this now because my replica is no longer connected. Okay. So what is happening to our offset? Here I'm at 1023, 1,000 less. But has the replica caught up? Let me do an info replication. Lag is increasing, and my replica offset is not catching up. It used to catch up before. Now it is not catching up anymore, because basically the replication is not happening, right? Now I have this continue replica. So it's basically now says, okay, replica, now you continue. Now if I were to do info replication on the master, look at this. Lag has gone back to 0, and the master and replica are happily in sync again, right? So we did introduce some instability where the partial sync actually worked now, right? That data was actually buffered on the master, and when network came back, it actually wrote that data. Now let's start to introduce bigger problems. So I'm going to stop the replica, and this time I'm going to load up so much data that I'm going to overwhelm its buffers. So I'm going to say load 10,000 keys. And I want you to take a close look also at our server log. So what did you expect to happen? As I mentioned in my talk already, our client output buffer was overwhelmed, and master decided, hey, client, you're too slow. I'm not going to store any more data for you. I'm going to basically close, right? Close this connection. So that's exactly what happened here. Now, again, pay attention to the server log on your top screen. I'm going to now continue the replica. And what do you expect this time? So the replica comes back and says, ask the master, hey, give me the data. But master rightfully responds, I'm unable to partially resync because of lack of backlog, right, as expected. And they go into this full sync mode. And now they're in sync. Are they in sync, really? So let's check. We're doing the info replication, and the offsets. Oh, it's still catching up, maybe. Yep, 6 to 1, 6 to 1. And the lag has come back to 1. So what we demonstrated here is partial sync. When it's possible, it works. When it breaks, it goes back into the full sync. All right? So next, I want to demonstrate the data inconsistency thing I mentioned. So I'm going to, for doing this, I'm going to start a Redis client session. And then I'm going to set a key. And I'm going to say, has my key reached one replica? And I want to wait for 10 milliseconds. OK? And what do you expect the answer is going to be? Because the full sync is now happening correctly, it should say, yes, one replica got your key. All right? Now, let's go here and stop replica. I'm going to now stop replica. And now write set, let's say, different key, v2. and I'm going to execute the same wait command this time. Remember, right now, sync is not happening. What do you expect the answer going to be? Let's find out. So it is 0. No matter how many times I try, it's going to be 0 because replication is not happening. Okay? So this, as a client, you're controlling, right? You wrote a key, and you can proceed only after that key has reached the number of replicas that you want, and this is the way for you to control it. And let's just finish the story here. So I'm going to continue the replica. And if I come back here, if I do the same wait command, what do you expect this time? The sync is happening. I should say, yes, one replica got my right. Okay? So what we demonstrated here is a way you can achieve best level consistency as a client using the wait command. And before I show the memory parts, the thing I want to show really quickly is switching the leadership, switching the mastership, and how it affects your second replica ID. All right? So I have this switch master. What this command does is switches the mastership from 7001 to 7002. But before doing that, it actually takes a dump of the info replication on the replica side, and it takes a dump of that after doing the mastership. And at the end, it switches the mastership back so that the demo can continue. So I need to mention, I want to switch the mastership to 7002. And let's go over here what happened in a minute. So it does a before dump. As I said, it was the old replica. And the replica ID, remember this, it starts with 4A. Rep ID 2 was 0, the default value. And offset was something that's ending with 753. And then it did the switch. So I invoked replica of no one and made 7001 the replica of 7002. And let's look at after look. You know what happened when I switched the mastership. So the new master got a different rep ID, but then it saved the old one in the master rep ID 2, and the offset was still stored as is, and the second replica offset was bumped by 1, and it's stored. The reason why it's +1 is when replicas come, they ask for the byte that they do not have it yet, which is the next byte. So it's going to bump up that number. From this point onwards, if I write new data, only master replica offset keeps moving, keeps increasing, and second replica offset is kind of frozen at this point. Okay? So what we demonstrated now is the uses of the second replica ID and the offset. So the last part of my demo, let's see how we are doing on time. Should be OK. The last part of the demo was the impact of memory, right? In order to do that, I need to put Redis in a no eviction mode. So I'm setting max memory policy as no eviction. What happens with this is Redis keeps taking the writes until it has enough memory. In this case, my max memory is set to 10 meg. And I want to see under these conditions how much data I'm able to write to the Redis. I'm going to start with a clean slate. I'm going to flush everything in my Redis Master. And I'm attempting to load 10,000 keys. And I want to see how many I'm able to write. So obviously, once the 10 meg limit is reached, I'll be unable to write those many keys. So as expected, I got a out of memory, and I was able to write about 8,300 keys. I cannot write anymore because the Redis became full, and I've set the max memory policy to be no evict. So that means it cannot take any more write. Okay. So now let me flush it. And this time, I'm going to change the backlog size. oh, a backlog size was a very small 16K for the first exercise. I'm going to now make the backlog size as 5 meg. And if you remembered my slide, if my max memory is 10, if my backlog is 5 meg, that only leaves 5 meg for the user keys. So if I were to repeat this load of 10,000, what do you expect? You expect less number of keys to be held in Redis. Let's see if that is true. Boom. I'm only able to store about half the keys because I consumed half of it by the backlog buffer. Okay, let's take it to the extreme. And this time, I want to set my backlog buffer size to 10 meg, which is same as my max memory, right? Let's do this. Let's do the flush. And at this point, I'm just writing a simple key 1 value 1. I'm no longer able to write even a single key 1 because even though I gave 10 meg, I consumed all of that with this replica backlog. So I hope it sticks in your mind that how replica backlog and max memory kind of work together. So let me set this back to some sensible number, which was same as before. So the last thing I'm going to show you today is the impact of the client output buffer on the process size. Again, going back to the slide, the client output buffers, they're not counted in max memory, but they keep increasing your process. So let's attempt if we can do that. So my current output buffer limit, this is the key number. This number actually controls, this command controls client output buffer for different things. But one that's starting with slave is the one for replicas. Currently, it's 16K. I'm going to change the output buffer limit to the default, which is 256 meg. All right. And I'm going to flush all, starting with a clean slate. And I have this command called churn. What it does is I give some number of keys. So this one basically keeps overwriting the key with same value over and over and over again. Redis doesn't know that the value is same. So the impact of this is it's generating a large amount of backlog very quickly. So your backlog gets full, your replica output buffer becomes full. So let's see when this is running, what happens to our process. And over on the top window, I'm going to do monitor my master. Monitor master is a command. Basically, I'm doing a top and grabbing the memory that's used by my master. Okay, so we are at 10 meg right now. And this is just for master, all right? Now I'm going to start churning. So I'm writing large amounts of data now. And what did you expect to happen for this, memory, right? It's kind of staying around 10 meg. It increased a little bit. The reason why it's staying around that is because your sync is happening correctly. There is nothing being kept, all right? So let's kind of let's be the bad boys and stop the replica, all right? And watch that number. Moment I stopped it, my client output buffer is, buffering this data for this client, which hasn't synced up yet. It keeps increasing. It goes up to 256 meg, and boom, it came down to 31 meg. Can you guys make a guess on why it came back? Reason is obvious. Because we closed that buffer, say, hey, client, go away. I don't care about you. And then it releases. And that can be evidenced by the master log, where it says, I'm going to close this connection. All right? So let me, again, continue the replica so it can do a full sync. And Redis is reasonably great at giving back the memory, but I would have expected the memory to come back to 10 or 11 meg here, but it's not, right? I haven't found answers of all the answers here. So there's still something that Redis is keeping. I think there's a scope for optimization here. Ideally, in my mind, if it was 11 meg before, I buffered something, send the data, now I no longer need the buffer, it should come back, but it hasn't. So now I'm going to attempt something very adventurous. Do not try it at home. So output buffer limit, I'm going to set to 0. What it means is I set no limit. Let the buffer increase as much as you can, right? So I set this, and nothing is happening to memory because the sync is in progress. So again, let's stop the replica. And this time, it's a recipe for disaster. It just keeps increasing. There's no limit. And then that's why I say never attempt this at home. I'm just giving a demo here. So I need to stop this pretty soon myself. Otherwise, my laptop will be no longer usable. So let me continue the replica. Yeah, and the memory came back. All right. So I hope I showed in a demo how the partial sync works, how it kind of falls back to full sync, what's the use of this secondary replica ID on a leadership change, how you, as a client, you can drive some of the data consistency parts and the relationship between the various memory and the buffers. All right. So let me switch back to my presentation. And if you like my talk, I just want to plug here that we are hiring. So please come and hit me up. Thank you, and 10 years of Redis. All right.